can see the slides. Next. So what is diathermy? It's a device which uses electrically induced heat to cut and or coagulate tissues during surgery. This is the application of diathermy. So we have monopolar and bipolar. Monopolar, you have seen there's only one pole, one end like a pen. It has two knobs here, one to cut, another one is to coagulate. So it can cut and coagulate. But bipolar, like a forceps, it has two poles, two ends. It only coagulate, it doesn't cut. Okay. Then you have your pedals, your leg pedals to cut in case of bipolar. If you want to use your, if you want a monopolar, if you want to use your pedals. Okay, if you don't want to use your hand but you want to use your pedal, you can just use this. Or you then you have a plate, earth plate, which is used with your monopolar and cables, and this is the machine that set your limit into coagulation. So you say monopolar, they will connect it here. This is your monopolar. You see, this thing goes into here, monopolar. If you go to the OT tomorrow and have a look at it, so monopolar, you look at the end of the plug here, it goes here. So that's why you have cut and coagulate. There are two different things. I'm sure none of you have noticed this before, right? So you can see this. Understand? And then you have a earth plate connector. You connect your earth plate. So this goes into your earth plate. Also for monopolar. Bipolar, you don't need earth plate. I will go into this. So all these are monopolar equipment. These four. You have two different pedals. Yellow to cut, blue to coagulate. This is universal. So yellow to cut, blue to coagulate, blue to coagulate. So it goes here, this thing. And then you connect your earth pedal. Earth pedal will be connected to space here. Then this thing goes in here. Okay, earth plate. The blue color pad that we stick to the patient's thigh or back and everything. Let's say you're using bipolar. Bipolar only coagulate. So bipolar, you see these two things. Got two things, right? These two socket, this two AUX kind of socket will go here. One for each pole, and this thing will be connected here. This end will be connected here. Go to OT tomorrow. Please have a look at it. Okay. This is one picture, explains it all. So one machine used for both monopolar or bipolar, different, depends on where you connect it. Next. Monopolar diathermy, bipolar diathermy. Monopolar diathermy, it uses a earth plate. So you connect the wire, the circuit completes in a one loop. It goes, the electrical current is passed through the wire, comes to the bipolar probe, diathermy, the monopolar diathermy. The heat is applied into the tissue to cut or coagulate based on whether you're pressing yellow or blue. And then the current F2 goes through patient body and then earthed via another cable that is connected to the machine. Okay, so it has to go through patient's body. It uses patient's body as a passage of current. Okay, this is earth plate is used. Bipolar diathermy, no earth plate. The current that comes from here goes to one pole, and the energy that transmits between the pole goes back via the cable to the machine itself. It doesn't pass through patient's body. That's why bipolar is safe. There is no current transmission via patient's body. It doesn't use our body as a passage. That's why bipolar is safe. But why we still use monopolar? Bipolar only can coagulate. It cannot cut. Let's say you have a deeper tissue, you have to cut precise, you have abdomen and everything. Bipolar, by only coagulating, your incision will be difficult, or it will take time, or it won't be precise. Monopolar can cut and coagulate. So it will be much easier and more precise and sharper incision. That's the difference. So one is more safer but less efficacious. Another one is more efficacious but less safe. That is the difference. So again, you look at it. When you use bipolar, your current transmission only stays among the tissue, one pole to another pole, between the two poles, two ends of diathermy only. It doesn't go down. In monopolar, you can see you apply it, you cut or coagulate, it actually goes through your body to reach the earth plate. So it actually causes more damage to the tissue. So monopolar versus bipolar, monopolar cautery, electrical current travels from electrode to the plate below. You apply the heat, it causes tissue coagulation or cut, it causes vaporization, devitalization of tissue and goes through. It causes heat around the tissues and then pass through tissue to reach the plate. But in bipolar, electrical current travels between the two electrodes alone. It's localized at the site of use. So I have this in my own notes where I have actually incorporated in tables all the potential MCQs. So circuit, monopolar, patient forms part of circuit, grounding pad, which is the earth plate, is needed. But in bipolar, energy passed between two forceps tips, no dispersive pad, not earth. Both uses isolating capacitor, high impedance to 50 Hz current, avoid microshock. As I mentioned earlier in electrical basics, AC current at 50 Hz is the most dangerous. So but this diathermy has a capacitor inside which produce impedance, which is resistance to this 50 Hz current to prevent microshock, because this part, the current is directly applied into your body tissues, right? So you have to prevent the microshock, not macroshock. Low impedance to high frequency. Okay, you see, 50 Hz current is low frequency. The impedance is to the low frequency, but they don't produce impedance to high frequency. That's why it allows the current to pass through. So quite difficult for you to get this point, but never mind. Just remember the upper sentence. Okay. Next, electrode. You have monopolar F, active and passive, and a dispersive pad. There's only one. The active is the electrical the pen-like end that touches the tissue. Your passive electrode is your pad. But in bipolar, both the forceps tips are acting as active electrode. That's why only current passes between these two. Local current density is higher in monopolar because it goes through the tissues, is dispersed. But in bipolar, it stays between the two electrodes because so the current density is lower. Power, you use higher power in monopolar, 400 watts. That's why you can cut because it's higher power. When bipolar is lower watts, so only coagulate. I put yellow for monopolar because it can cut. In bipolar, it can only coagulate. That's why I color it blue. As I mentioned, monopolar can use B to cut. Bipolar cannot cut. Coagulation, in vessels only less than 2 millimeter, it can coagulate monopolar, but bipolar can coagulate better in larger vessels. Okay, it's better for coagulation. During monopolar is cutting, it causes alternative continuous sine wave. Okay, remember this continuous sine wave. Okay, but in coagulation is short burst, damped or pulse sine wave, pulsed. This is continuous, this is pulsed. Okay. EMI is electromagnetic interference, mean it can catch up your ECG, it can catch up your pacemaker, it can catch up your defib, all these things. This is your, the EMI is more in monopolar because it's higher volts, higher current density, lesser in bipolar. That's why in a patient who have heart problem, who has pacemaker, we doesn't allow them to use monopolar. Safety, risk of VF, wet service, less risky. Collateral tissue damage, as I said, the current pass through more tissue, it causes more damage. In bipolar, is less damage. Advantages, this is again the same here. I've summarized it here. You can just see it there. Again, repetition. Just look through this. So monopolar, the current pathway is from electrosurgical unit via the patient's body, go to the return pad, then goes back to the electrosurgical unit. But in bipolar, electrosurgical unit, patient tissue, electrosurgical unit. It doesn't take a longer route to reach it. Okay. Again, bipolar, you can see the current comes from here, go to the tissue. It just go between the two electrodes and then goes back to the electrosurgical unit. But monopolar, it comes one way, cut, goes through patient's body, go to the earth plate, then goes to the electrosurgical unit. These are just repetition. Look at it on your own pace. Again, repetition. You can see monopolar, bipolar. This is monopolar. You have a earth plate and everything. Then your bipolar, ground reference and isolated. So never mind. Just go through it later. These are few MCQs. Later you can go through. So next we go to ultrasound. Understand better on diathermy. Any question? This should be enough for our level lah. We are not the person we use diathermy. We are the person who has to know about diathermy because in OT, the surgeons are using. And we should know when to allow them to use monopolar and bipolar. That's the main thing. Okay. So you have to make sure the earth plate is well prepared. It might be a bit redundant, but all these are our fault, you know. Let's say a patient got electrocuted because the earth plate is not placed well by using monopolar. Rather than surgeon, when in a court of law, medical legal case, we will get sued also. Because patient safety in OT, 99% is NS role. 1% only surgical. Because SSSL is also a anesthetist role more than surgeon. Of course, surgeon have to present also. Like let's say that the case that recently happened because of your lignocaine allergy. The fact that we let the houseman put in the CBD using a lignocaine gel without informing the other team is actually our fault. It's NS who actually should have made it we made it a role that you put it in the board that patient has lignocaine allergy. Tell the whole team, including your scrub nurse or your GNS, that these patients have LA allergy, do not use lignocaine. It's actually NS fault. Okay. Of course, the person who done it, a surgeon also have a fault that they are not around during the SSL, but that will go back to NS also. Why did you start the case without the surgeon being present at the during when you do SSSL? Okay. So all this you have to take into account. So next we go to ultrasound. In terms of ultrasound, again, what is ultrasound? Ultrasound is a medical imaging technique that uses high frequency sound waves. High frequency sound waves and their echoes means the direct waves that goes from the machine to the patient and reflected waves, the echoes that come from patient to the machine back. Okay. Human here only can hear a sound wave of 2 hertz to 20,000 kilohertz. Okay, 2 hertz to 20,000 hertz, which is 20 kilohertz. 2 to 20,000. But ultrasound give ultrasonic wave, higher frequency of megahertz, 1 to 5 megahertz. Our medical ultrasound uses 2.5 megahertz most of the time. Ultrasound got medical and non-medical. Even in other application in industrial, they use also ultrasound for something else. Those who are in environmental also use ultrasound to detect water source. So all these even uses even higher megahertz. But in medical ultrasound, usually it stays around 2 to 2.5 megahertz. Okay. Sound waves hit boundary or air between tissues and bounce back to probe. The CPU or central processing unit, the machine itself, which incorporates all this electrical and softwares inside, calculates the distance from the probe to boundary using speed of sound in tissue and echoes return to display an image. I'll go in detail. So if you see your ultrasound have a monitor, this is the monitor and your central processing unit within this, and your keyboard, storage device, transducer probe, printer, all are connected to your central processing unit. So this is where your electrical signal pass through the probe, where it will produce ultrasonic sound waves. These sound waves in touch with the patient's body will transmitted through patient's body into the organs, and depends on the organs of interest, it will bounce back. That's the reflected waves which comes back to the transducer and go through cable to the CPU, where these multiple waves are changed into a dots, and in a whole process it comes to reflected as a whole image. Okay. Let's look at it here. This is your transducer probe, sender or receiver, sender lah. So it sends ultrasonic sound waves. When it's an organ, it reflects back. This is the original wave, then your reflected wave. The reflected wave received at this end and sent to the one. depends on the distance of the sound wave sent and the reflection. There is a time. If it's further beyond, let's say you put in an abdomen, if it goes all the way beyond to your peritoneum and below to your spine, it takes longer time to hit that part and comes back. So that will say the time that taken to reach back, the reflected wave to reach back, is corresponds to the depth of that organ. If it reach back early, it shows as it is a nearer organ. So let's say you put your femoral line, right? You put it, initially you feel it, the subcutaneous skin, subcutaneous tissue, and your artery and vein. If the artery and patient is more big, it will take you will see the depth of the vein or artery is even below. That's why it appear. So the object that are near, the tissue organ that near will appear brighter, more brighter, because the wave reflects faster. So it more brighter compared to the one at the more deeper level. So the one that near appear brighter, the one that's situated lower will appear darker. So we have first, the most important component of these all is the transducer, and that is the most expensive also. So that's why we have to take care of the transducer very well. So we have multiple types of transducer. You all just can look through here. Okay, we have linear, curvilinear, pulsed array, and now we have a multi-phase transducer. The new ultrasound we bought, the Cosmos, uses this multi-phase, one for all. So different transducer have a different frequency, and when you have a different frequency, they cause difference in resolution and penetration. Okay, you can look through here. Basically, your linear probes are higher frequency, 7.5 megahertz. You can see this. And your curvilinear probe is the most lowest frequency, 3.5. Okay, you can look at here. Then your phased array probe is your echo. Echo also actually low frequency lah. Okay, the highest is your linear array probe, which is high frequency. High frequency is good resolution but shorter penetration. That's why you can use linear probe for abdomen, because it needs a increased depth, increased penetration. You have to use a curvilinear probe. But when you use a curvilinear probe, the image is not very clear because it's not a higher resolution. Let's say you want to do a block at the supraclavicular. You need a good resolution to identify the nerves and vessels. That's why you use linear probe, and you expect the supraclavicular block is a superficial block. Let's say you want to do a lumbar block, which is a deep block. You can't be using, or quadratus lumborum, you can't be using linear probe because you need a depth more than the resolution. So you have to choose your probe accordingly. So what is it in the ultrasound transducer probe, which makes it very special and very expensive? So you have your acoustic insulation, the place you probe. So at the end of it, at the tip of it, you have an important component called piezoelectric crystals, which emits piezoelectric effect. In which, what is the importance is, it actually transmits the crystals. The electrical signal that comes from the cable here, from the power source, will cause these crystals to move, to vibrate, and produce ultrasonic sound waves, which pass through here. So arrangement of piezoelectric crystal, you can see here. The electrical signal will cause the movement of these piezoelectric crystal, movement, which is vibration, and causes ultrasonic sound waves to be produced. So look at it. Your ultrasound machine, the electrical signal comes, your piezoelectric crystals will cause ultrasonic wave, produces, because the vibration of it causes ultrasonic wave, and it echoed back. This is your reflected sound wave, come back to the piezoelectric crystal and transmitted to your ultrasound machine. So piezoelectric crystal emits ultrasound waves. The ultrasound wave returns from organ, creation of ultrasound image on the screen. Application of an electrical current to the crystal causes it to vibrate, thus generate ultrasound wave. Reflected sound waves hit the crystals, causing it to vibrate and generate electrical current that is analyzed by the ultrasound machine. So electrical current hits your piezoelectric crystals, causes ultrasound waves, goes into the body. It reaches the organ, bounce back. The reflected wave comes back as a wave to reach the piezoelectric crystal. Piezoelectric crystal will again vibrate, convert this kinetic energy of your movement of your ultrasonic wave into electrical signal, goes through the cable to your ultrasound machine, CPU, to create the image that we view on the screen. This is the repetition that I mentioned about the probe. Higher frequency means shorter wavelength, less penetration, but better resolution. Lower frequency, curve probe. This is your linear probe, your curve probe. Lower frequency, longer wavelength, less attenuation, less penetration, less resolution, but greater penetration. Okay, remember this. Next, we go to the modes. The simple modes that we use is ABM mode and your Doppler mode. We have few different. So this is a simplified. For the simple thing we use, A mode is the simplest mode. Uses single transducer. B mode, multiple transducer. M mode is motion. More in detail, A mode is an amplitude mode. Amplitude of the reflected ultrasound is displayed on an oscilloscope screen. This is the one we usually use. Then we have your B mode, brightness mode, 2D in echocardiography. This is now the essential imaging modality in the diagnostic ultrasound. And amplitude of the reflected ultrasound signal conveyed into a grayscale image. So this is the one we use lah. Whatever the mode, whatever the bounce wave comes back to the CPU in a multiple dots, conveyed into one processor and reflected as a grayscale image. If it's nearer, it appear brighter. If it's deeper, it appear darker. What type of tissue causes what color changes? We'll go through it in detail. D mode is the Doppler mode. Doppler mode is for your imaging based on the Doppler effect. Change in frequency, Doppler shift caused by the reciprocal movement of the sound generator and the observer, like in your fluid movement, your R3 and everything lah. Okay. So there is a repetition. Just want to say M mode is a continuous movement of your B mode. When you set B mode, let's say most of the time, if you want to show sliding sign or anything, you just put your ultrasound initially. You look at your B mode first, sliding sign. Then you want to show your seesaw sign, or you want to see your transition point or lung point, you go your M mode. Okay, that's the difference. Then your Doppler, when you measure IVC also, right? You initially start in your B mode, then you go to your M mode to measure the diameter. So Doppler mode is for when you want to see your, let's say you're doing a femoral line, you want to see which one is artery or vessel, you put it to find your Doppler mode. So Doppler mode got two color, red and blue. It doesn't mean red is artery because the color of the blood in the artery is more red and the vein is more darker. That's why it's blue. It's not like that. Red means the flow is approaches the transducer. Like artery, the blood flow is towards your transducer. Vein is away from the transducer, right? Blood flow away from the transducer, right? So that's the idea of it. So this is the tissue difference and the color. If you have a fluid like blood or your pleural effusion or anything that blood, it will be darker, black. The denser material, it is more reflex though. When you have a dense material like a bone, it will reflect the waves more strongly, bounce back more strongly, and it comes faster. It reaches your transducer back faster. That's why it's brighter, like your bone. You see your bone appear more white, more bright. But if you have a fluid, they only bounce back slowly. The reflected waves comes back to the crystal slowly. It takes longer time. So that's why it's less bright. Okay. So the denser material is the more it reflects the sonographic wave. Fluid like blood transmits ultrasound waves and a minimum waves reflected back. This yields a black and echogenic image. Stones yield a white images with a white shadow with them. Soft tissues like liver, different gray color shades. So when you have a very dense material like bone, it will be very bright. You have a solid organ like liver, all these are in between. So it comes in a gray scale. When you have a fluid, which is as a very less dense, they only reflect the waves very slowly. That's why it's appear black. Okay, that's all about ultrasound.